It's my great pleasure to have Lan-Hsuan Huang, who recently just gave a mini course here from UConn, and she'll be talking about null perfect fluids, improvability of dominant energy scalar, and Bartnik mass minimizers. Lan, please.
All right, so thanks Martin, and thanks organizers for putting this conference together. It's really exciting to see many people in Relativity and working on very impressive results. So in this talk, from the title, I will talk about null perfect fluids, improbability of dominant energy scalar, and Bartnik mass minimizers. So it looks like a three very different topics, and I hope you will see there's an interconnecting relation between these three. And the talk is based on a joint work with Dan Lee, who spoke in the conference on Monday. And more precisely, this is from our paper posted in arXiv about 2 years ago, and it's to appear in Journal of Differential Geometry. So let's get some backgrounds, right? So modify, we want to talk about modify constraint operator. But first, what would be the usual one? So the usual the usual constraint operator is really if you look at space-time, and then you take a slice, a space-like slice, and then you have the initial data, which is an induced matrix and induced second fundamental form. And so we like space-time to have the Einstein equation satisfy some condition. So the Einstein equation reduced to the slice give a meaningful so-called constraint map. The constraint map is essentially just the Einstein equation together with the trace of the Gauss equation and then Kodazzi equation. But it's interesting, it can be written complete in terms of G and K, the induced matrix and second fundamental form in this form. So the first one is a scalar function. This is a half times the scalar curvature minus the length of the K. So K is a bilinear form, and then the trace of K squared. And the second term is a one form, it's a divergence K minus the D of this trace K, and which is also denoted by mu and J. So we define a modify operator, right? Even before I tell you why we do that, let me give you a definition. So it's really, we fix a background initial data G and K, and then we use it to modify the constraint map. So it's in my work with Justin Covino a few years back and published in 2020. And this is defined of the similar type as the usual constraint map. So for given initial data gamma and tau, we first output this, use the usual map, but then we modify it by adding a term which is linear in gamma. It's actually only defined on gamma. So this is going to be, so the first component will be 0, and the second component is a one form, is the gamma, which is a symmetric to tensor contracted with J, and the J is the background J. So it's a J with the subscript of the background G and K. So this is really just a linear term in gamma. So why bother? So it actually turns out we introduced the concept trying to understand the dominant energy condition. The dominant energy condition for the initial data says this quantity mu and J are related by this inequality. So mu is greater or equal to the length of J, and J is the length taken in the matrix G. And so like me, I study initial data sets, and we really need some condition. The most often we assume the initial data set has to satisfy dominant energy condition in order to prove anything meaningful. But it turns out it happens a lot is we want to modify our initial data. But then the question is whether the dominant energy condition will be preserved. And that's really the main motivation we introduced the modify operator. It's used to preserve the DEC, the dominant energy condition, when we perturb GK to a nearby gamma and tau. So there are many different ways essentially will satisfy this property. One example would be if we have a G and K, which already satisfy the dominant energy condition. And then if we consider the level set, which are those initial data, which has the same modified value as G and K, and then we can see there's a neighborhood in like some abstract space of asymptotically flat initial data sets, or even doesn't need to be asymptotically flat, it's just really just a local result. So just some space of, this is some gigantic space of initial data sets. And then this level set has the property if G and K satisfy the DEC, and the nearby one will also satisfy the DEC. But this is not clearly, it doesn't seem to hold for the unmodified operator unless G and K is vacuum. And the reason is, really think about for the modified operator, you have the freedom to choose probably prescribe phi. That means you can prescribe mu and j. But then this inequality actually involves taking the length. And G is something usually you cannot prescribe. And the modified operator has the effect which will do this thing G and J together. So this modified operator is quite useful. We have used it in several results. Even before we define the nonlinear operator, the modified operator with Justin Covino, the linearized version is already appeared in my work with Mikhail Eggemeier, Dan Lee, and Rick Shen, when we proved the positivity of mass for initial data set with DEC. And in the work there, we need to develop some density theorem. We want to simplify the asymptotics by the harmonic asymptotics. But then in order to do that, we also need to bump up the dominant energy condition to be strict everywhere. So in that work, we already have a linearized version of it. And so the density theorem extended the result of earlier work for vacuum case. For vacuum, you can work with the usual, the classical constraint operator. And there's also recent work by Dan Lee, Martin Lasud, and Ryan Unger. They extend this work for the case with boundary. And with Justin, we are really thinking about doing gluing results. We know there is a beautiful gluing result for vacuum. And for vacuum initial data set, you can change the asymptotics to be curved, exactly curved outside compact set. So wanted to do that for general DEC. And then, so that's why we come out this modified operator. It turns out the extra term is a lower order. So it's really inconsequential in those analytic framework of Covino-Shen or crucial delay where they do vacuum gluing. So, so our results just very similar analytic part. And the result is given an initial data set with DEC, we can glue to a curved solution, which is vacuum, through an interpolation region, which satisfies the DEC. And also we use this define the modify Regge-Teitelbaum functional. And that's in my work with then we try to prove the equality case for the positive mass theory. We want to say if you have an initial data set with DEC and has E equals P, E is the energy, P is the momentum. And then we want to say the slice is actually has zero energy and momentum. So it's in Minkowski. So there we use the modified operator to define this Regge-Teitelbaum functional. So we will come back to this equality case later, but probably just let me mention there's a lot of results on the equality case, including by crucial and in the higher dimension. Also, there is a really beautiful recent work of Svan Hirsch and Yi Yuan Zhang. They proved the equality for 3 dimensions using the level set method based on the positivity result in the Hirsch, Kazaras, and Marcus Curry. I think probably Dimitri Kazaras will mention some in his talk, in next talk. So we see this very useful. At least we have been using proof a lot of things. So what will be most relevant is the linearized operator. So here we have a background G and K, and we define the modified operator, and we are going to linearize at the background G and K. So we will not get rid of the subscript G and K here, which is denote this linearized operator. But in fact, we're actually looking at more the adjoining operator. The adjoining operator we denote by this star. So it's really integration by part to the pairing function. So the formal adjoining operator. The adjoining operator acts on a pair of scalar function and a vector field, F and X. And we're looking into the kernel of the adjoining operator. In the case of vacuum initial data set, this our modified operator becomes really the usual operator. right? So this is only really interesting, give some new thing when initial data set is not assumed to be vacuum. So the solution or the kernel element of this modified adjoint, or either the unmodified one, falls in the category of so-called killing initial data named by Bike and Kushel. So why is it called killing initial data? Because it does give you a space-time killing vector field. So what they discovered is you can use this, so also called the lapse and shift, F and X. In the case when F is not 0, then you can use it together with the initial data to construct a Lorentz space-time, so which is called the killing development. And in that killing development, you write down a vector field using F and X. It will be a killing vector. So this really has a more classical result. So they define it in 1996, but in Moncrief, you already give this concept in 75. A very classical result is now we're looking at, suppose the initial data is vacuum, right? So the size is vacuum. And then if it has a non-trivial, this F and X, the killing initial data, this is if and only if the vacuum development has a global killing vector field, which exactly has the lapse F and the tangential vector X. So that's a one-to-one correspondence. So in other words, when the initial data set is vacuum and any kernel element here really correspond to a unique killing vector field of the space-time and vice versa. But why do we care about this adjoint kernel? Because around the same time, when Fisher and Marsden, they study the scalar curvature deformation, and at that time, I think people are really interested in related to Nuremberg's conjecture, is you want to somehow prescribe scalar curvature, right? And extending their earlier work, they want to say, can we prescribe the vacuum constraint equation for general initial data set? So for that purpose, they prove this theorem. So suppose if U is compact manifold without boundary, and then if this adjoint has trivial kernel, then it's direct to see the linearized operator, not adjoint one. The linearized is surjective. So the nonlinear map is locally surjective. Once it's locally surjective, and that really helps them to solve for vacuum initial data. In the case when U has non-empty boundary, is much harder. It's been done in the work of Covino-Shen, based on the work of Covino for the scalar curvature, also in crucial delay. And what we do is, essentially we say the same analysis holds for the modified operator. So that's with the work with Covino. So why we care about this locally surjective? Because very related to my earlier comment is the level set given by this modified operator will give you initial data set with the dominant energy condition. All right, but now in view of this Moncrief's theorem, it tells you the kernel element is actually something really meaningful, right? So the natural question would be, does the kernel space of either one, either the usual, the classical operator, or the modified operator for general initial data set, which may not be vacuum, have any physical meaning? If it's vacuum, then we have the result of Moncrief. And now it's like generally we know this operator is helpful even for non-vacuum initial data set, and what would be have any physical meaning? So let's get to the main first item of the talk. So I forgot to mention, like, please stop me if you have any questions. I'm happy to answer any questions. So this leads to the first topic about no perfect fluid. So back to that natural question, still we don't have the answer yet. But then this study in the following slides, you will see, actually you are going to looking at a further coupled equation that will have more physical meaning. So before we get to that, let's define not perfect fluid. Probably it's a review for some of you. It's a space-time, and it's called not perfect fluid. And we say we have a velocity v. So v here, we require it to be future null or zero. So if v is time-like, is usual the perfect fluid, but we say not perfect fluid requires to be future null or zero. It could be zero. And then it has the pressure P. So if the Einstein tensor satisfies this equation, the right-hand side, the matter field satisfies this equation. That's the proportion by pressure of the matrix plus the tensor product of the velocity V. So it does include several special cases. For example, when P and V are zero, it's just the vacuum case. But if V is zero, P is constant, it can also be interpreted as the vacuum space-time with a cosmological constant. And in the case when P is zero, we only have a V, it's called the no dust. So essentially, we find out we can use the modified operator or the kernel space of the modified adjoint will give you some meaningful interpretation for the initial data set inside a not perfect fluid, but not the general not perfect fluid. It's a special not perfect fluid, which has a global killing vector field Y. And in addition, the Y is related to the velocity V by some function eta. So in the case eta is not zero, that means the killing vector has to proportional to V, so it has to be null in particular. And if eta is zero, we don't really have any causality condition on Y. And of course, you want to ask, are there any interesting examples which is a not perfect fluid also satisfy this kind of strong condition, right? It has a global killing vector field and a vector field related to velocity in this way. So it's actually, we found out there's a big class of examples. They're called PP waves. So PP waves are in particular no dust, P is zero, and here V required to be covariantly constant. So in other words, the covariant derivative of V is zero. So in particular, V itself is a killing vector. So this condition automated holds. And there are many, many examples of different matrix satisfy this condition. So the following slides, I will give you characterization really in analogous to Moncrief's result we mentioned earlier. So first, if we give a not perfect fluid with velocity V and pressure P, and assume there's a global killing vector field Y, and V and Y are related by a function eta, then what can we conclude? We say there's for any space-like hypersurface inside. So for any initial data set, space-like hypersurface inside. And if we decompose the killing vector field into the labs and shift F and X, then this will satisfy this equation. So you will be the kernel of our modified adjoint. And furthermore, we actually have this equation. It tells you F and X has to point in a very special direction related to J. And this equation, we give a quite fancy name. We call it J null vector equation, because it says in particular Fx, the vector Y will be null in the case J is not zero, and it will point to the direction of J. And also we show that under this condition, the pressure function P must be a constant. So you can think about this as a one direction of Moncrief's result. You have to have a vacuum space-time, and the killing vector field on the initial data set satisfy a special equation. And we also have sort of converse result. If we have initial data, which admits a non-trivial kernel, and here we have a condition F is not zero. I will talk about the footnote very soon. But then we show Fx satisfy the system is an adjoint kernel and satisfy J null vector equation, the system we call star. We'll also use this star notation throughout the talk. So once we have this initial data, and assuming the lapse function is non-zero, then we can actually, using the bicrucial construction, we construct a space-time called the Killing development. And furthermore, we find out that Killing development will be a non-perfect fluid. And that has a Killing vector field, Y. And moreover, all the quantity, pressure P, and the vector field V, the space-time quantity, can be written purely in terms of initial data. Okay. And moreover, if we know the initial data satisfy the dominant energy condition, then the space-time, the Killing development also satisfy the dominant energy condition, the space-time dominant energy condition, which is stronger condition, right? Which require the Einstein tensor if you insert any future causal vector is non-negative. While this just means you restrict the normal vector of the slice with another causal vector is non-negative. So this is a stronger condition, but we have the space-time will satisfy the dominant energy condition. And also very interestingly, we're able to show this quantity, mu minus J. So really it's just a difference of these. Mu minus the length of J is constant. So this is quite surprising. So somehow this is kind of long sought after property, really motivated by the Riemannian case, which we'll see in the next slide. But surprising is like this is a quite non-regular quantity because this is like a absolute value, right? So in general, this quantity is not differentiable. Probably only Lipschitz when J has 0. Right? But somehow this quantity is the one which remain constant. Okay, so back to the first note. So later in the slides, we'll see the result. We can drop this assumption. And that's usually in the case if we know, although F is 0, but if we know this equality holds, mu equal to J identically, especially that will happen when we know we are looking at asymptotically flat case. And if this equal, then we can actually further show by really mysterious relation from this condition, this system. And we can show G and K is vacuum. And then in that case, we can just use the vacuum development of Schoke-Brucha together with Moncrief's result to get this property. And then we can patch together along where F change sign. And this for the constant, we will see the remark in the next slide, really is just a reminiscence of the Riemannian case. So in the Riemannian case, we assume K is 0. Okay. So when K is 0, and then although I really have never write down what the definition of what the computation of D5 will be, but then in the Riemannian case, you'll see the first component reduced to the minus Ricci of the matrix and Laplace of Hessian minus the Laplace, Hessian of F, and then Laplace of F times the matrix, right? And then the second component is identically 0 when K is 0. So this is in fact just a operator on F. And the first component is exactly the adjoint linearized scalar curvature map. So in the case, there's a non-trivial kernel. This matrix is also called static vacuum, and it has very interesting relation to all other fields on study of scalar curvature, and it has a particular consequence if you have non-trivial kernel. Thus, the scalar curvature must be constant, right? So it had been a long time people wondering what would be the analogous property for the initial data set. So what we find out as a byproduct of this work is this quantity will be really the somehow the correct generalization of the Riemannian case, the scalar curvature to the initial data set, and we show this is constant. Right? So that's the first topic about non-perfect fluids. And then we will see why it has anything to do about this name probably you never heard about before, improbability and the dominant energy scalar. So the dominant energy scalar really related to dominant energy condition, and which we define. So in view of what would be the correct generalization of the scalar curvature, right? So we define the scalar function in this case to be mu minus the length of J. And then, so earlier I say in many cases, we want to somehow make the dominant energy condition strict. So it can be also formulated in this improbability. So we'll say the dominant energy scalar, this scalar function is improvable in this following sense. So if you have some amount of U, you want to bump up your dominant energy scalar. So it's more interesting when U is compactly supported, and then you want to find the deformation of the matrix H and W to be also compactly supported. It turns out to be a harder question. So we say this dominant energy scalar is improvable if for any U sufficiently small compactly supported, you can somehow perturb this data G and K by this amount, could be very small amount H and W, such that the dominant energy scalar is greater equal to the original one plus this prescribed amount. And most cases will apply when U is positive somewhere. So then that illustrate in this picture, we can bump up the dominant energy scalar. So in particular, if this is already non-negative, so GK has a dominant energy condition, probably you want to make U positive in the region you want it to be strictly positive, and it tells you can find the nearby initial data, which is strictly positive there. So we define improbability, but what's really we'll use most often is the non-improvability, because non-improvability helps us to somehow characterize the initial data set. And if I rephrase the result of me with Covino on the local subjectivity, we can also, using this new term of improvable, our local subjectivity theorem can say if the modifier operator is locally surjective, then the dominant energy scalar is improvable. Because if locally surjective, it's really like you can prescribe some amount and you find this deformation H and W to realize that amount. And then by doing some computation, that will achieve improvability. So local surjectivity of this Y bar imply improbability of sigma. But then we want to take the logic negation, right? What we'll say about non-improvable. So if this is non-improvable, so that means this phi bar is not locally surjective. And then back to our local surjectivity theorem, that means the adjoint must have non-trivial kernel. So this is just using logical negation to rephrase our earlier results. And as I mentioned earlier, there's an application. Once we use the modifier operator, even we don't know what the physical meaning of this kernel element will be, we just need to know it's a finite dimensional thing. And then we can, similarly as the vacuum case of Covino-Shen and crucial delay, we can do the gluing over annulus, and then we can use the finite dimensional freedom to match the Poincare charges of the gluing, like a Kerr solutions, admissible solutions near infinity. Okay. And really the most striking thing we feel like in this particular work in the small recent work with Stan Lee, which I put the year 2022, is we find out there's a further condition to characterize a non-improvable initial data set. So if this is not improvable, then by the previous result, we know there's a kernel element. But it turns out we can further show the kernel element is very special. It satisfies this further equation, this J null vector equation. So that's the same start system as the one which we have characterized related to null perfect fluid. So I have told you a lot of results, right? So putting these two topics together for null perfect fluid and then the non-improvability, what we can get is this consequence. So if G and K is the initial data set such that this dominant energy scalar is not improvable, and if F is not 0, then we know the initial data set actually sit inside a null perfect fluid space-time. And the constant, the pressure has to be a constant. And then we know the space-time has a Killing vector. And moreover, the pressure related to this quantity, and we know the dominant energy scalar must be constant. Right? So this will be really the proof of this. To get this one, to squeeze out this one extra equation is probably really the key, the most technical argument in the paper, right? So it's also the only proof I will mention in this talk. So let's look at a couple slides to just describe the idea of the proof. So the idea of proof comes from this observation. So we already have this modifier operator, right? It turns out this particular modifier operator is actually just one of an infinite dimensional family of the modifier operator, which make things work. So to see that, we find out we can use any scalar function phi to further modify the modifier operator. So this phi bar is the modifier operator at G and K, right? And this, if you cover this term a lot, you just take out this one. This is the modifier operator. But then we add additional term using the scalar function phi. It can be any scalar function. And then we add this term in this kind of weird combination of the quantity. And let's look at this. So all this term is going to be linear in gamma. Actually depends only on gamma. For the input gamma and tau, it depends only on gamma. J is the background J. So that's the J of G and K. And this is just, you take the computed length square using this input matrix gamma. And then this is just some quantity, the length of G, length of J by G, and then the tensor contraction of gamma, the input with the J of the background. So the reason why we can add this and why we need this kind of strange combination is really we want to make these extra terms to cancel out when we're looking at linearization of this dominant energy scalar. So this requires some computation, but it turns out, although we define the operator, it's a vector value operator, but when we compute the thing we want for the scalar function sigma, it turns out this extra term would cancel out. And the observation is, since we show that the modifier operator satisfies the same local surjectivity theorem because the extra term is lower order, is inconsequential. And the same thing holds for this phi modifier operator. So the observation would be if G and K is not improvable. And earlier we show it's non-improvable, then the modifier adjoint has kernel, non-trivial kernel. But then they say if this is not improvable, then in fact, for every phi, this phi modifier operator, it has a non-trivial kernel. So we get a lot of operators which are all non-trivial on this initial data set. And look at the adjoint operator of this phi modifier operator. So it turns out by computing it, it will relate it to the adjoint of the phi bar. And with this term, phi, and you can see here is really the J-Null vector equation comes in. So if it's non-improvable, then for any phi, there's always a non-trivial solution. So that means you can set this equal to 0. So this right-hand side will equal to 0. And that tells you for this fixed operator, there's a lot of special function f and x satisfy this equation equal to 0. And this equation is very elliptic. So we will expect that cannot happen, right? Very elliptic in the sense is a over-determined elliptic system because if you write down it's the Hessian equation of f, and this is the lead derivative of x on G. So possibly we can use some big theorem like probably Morse-Star theorem or the transversality theorem in global analysis to show it cannot happen, right? So you cannot have every phi, this is equal 0 unless this extra term really isn't there for any phi. So which means the fx has to be 0 and the fx has to be a kernel of this. although possibly there is some more abstract theorem we can apply to get that result, we actually prove this using really elementary method, but with a lot of computation there. So the computation comes in is we assume we have a non-trivial kernel, or assume we have a solution fx could be 0 or not to this equation. So this is a differential equation, but it has a very special structure. Is if you differentiate higher order terms, you get higher order derivative of f and x, but it turns out it can be written in the lower order. So by doing enough derivative and then replace all the higher order terms by the lower derivative of f and x, we can get a linear algebraic system when we write down in local coordinate chart. And this system also has a property. The solution here really is determined by the first jet of f and x. So it only really is because it's overdetermined. So it really only determined by a value f and the derivative, and also the vector x and anti-symmetry part of the first derivative at one point, right? So then we can get this a linear algebraic system, which will have a square matrix Q here, and then acts on this like one jet of f and x equals 0. So here Q phi is going to be a square matrix, and of course it depends on phi as indicated here and the derivatives, but also depends on G and K, the fixed initial data G and K. So this thing will be extremely hard to write explicitly because you involve like a lot of curvature terms and derivative terms. But fortunately for this special case, we can actually keep track of phi. So by keep track of phi, we can derive that for generic phi. So this can be made precise in our paper. For generic phi, so either this matrix is non-singular. So this matrix is non-singular, which means from linear algebra, you know, the only trivial, the null space is trivial, right? The only solution will be this order identically 0. If this coefficient matrix is not non-singular, that means the kernel elements, any kernel element must satisfy the J null vector equation. Okay. So then in our case, we know it's not improvable. So it must have kernel, right? And then that means the kernel elements must satisfy the additional J null vector equation. And then we plug in back here, and that solution, because this term vanished, must also be the kernel of the phi bar, the modify operator. So we could do that locally, because then we can write down this in the coordinates and keep track of the derivatives, but then we also have a patching argument to globalize the result. Okay. So that tells you we have characterization of the, sorry, back to this result. It tells you characterization of the non-improvability. Right, so that's the result here. So this tells you if we are somehow encounter the situation, which we'll see later, we really have to work on non-improvable initial data set. Then that initial data set has to be highly special. It will have a non-trivial solution, a pair f and x, satisfy this system. But then the similar arguments also allow us to show for general, any initial data set is almost improvable. So this says can be any initial data set. We can always, then I will go back to the statement here, but it says we can always bump up the dominant energy scalar by some prescribed small amount U at expense of some error term delta, which can be small, can be arbitrarily small, and over the region B, which can be arbitrary arbitrary region you decide. So this statement say given any ball in, so sorry, this should be U inside in manifold, And for any number delta, which is very small, can be small, and then we can find compactly supported perturbation, such as the dominant energy scalar is greater or equal to the original one plus the prescribed amount up to this error term. So this proof, it really follows the similar way, but we will even go beyond. We can introduce even more modified operator by phi and z here is to replace the role of j there, and z here will be choose to be supported in B. Here is where the error term will come in. So this can be viewed as, so in Locham's paper, he has a result. If you have, for the initial data set, you have a dominant energy scalar strictly somewhere, and he showed that you can actually do a conformal change by choosing a very delicate conformal factor to bump up the scalar, dominant energy scalar positive everywhere. So this you can view also as a different proof of that result. Okay, so let's go to probably the third topic about Bartnik quasi-local mass. Okay. So before we mention why anything we talked about earlier has a relation to quasi-local mass. First, what would be the quasi-local mass, right? So we already heard in several talks. So roughly speaking, you'll be for a compact initial data set with boundary. And you want to give a number, it's called the quasi-local mass should be as a number, and that will measure the total mass enclosed. So it's very highly motivated by the ADM mass for isolated system, which evaluates at the complete manifold and also for the corresponding hyperbolic mass. And this quantity generally defined using the boundary geometry, like induced matrix, induced mean curvature. But somehow explicitly or implicitly, it has to respect to some reference global geometry. So there are many, many notions. The one we'll really talk about is Bartnik quasi-local mass, but there's also a lot of Brown-York, Hawking, Horowitz, Wiscon isoparametric mass, Liu Yao Penrose, and in Pony Chen's talk earlier in this conference, he also mentioned about the Muzhao Wang and Professor Yao's quasi-local mass, and I think you will hear more in Yekai Wang's work where they able to use this concept to define a lot of different quantities, including angular momentum. So here I will focus on Bartnik, the definition. So in 1989, Robert Bartnik defined the Bartnik, now we call the Bartnik quasi-local mass, by this idea. So this is a compact region with boundary, right? And I think it's also in terms of history point of view, remember this was really during the time the breakthrough in the positive mass theorem was just done by Shen and Yao and later by Witten. And so I think he must came from the idea like there sounds beautiful theorem, positive mass theorem, let's apply it. So he want to define the quasi-local mass for this boundary region. So he think about how about let's extend it to make it complete with asymptotically flat end. And there we can compute the ADM mass, which is defined to be the Lorentzian norm. So E squared minus P squared, take a square root. And then we define to be, of course, it's, there are many possible extensions. So let's take an infimum. Sorry, let's take an infimum among all possible extension. And we also require the extension to be admissible. So everyone has a different way to define this admissible family. But there's some key conditions we need to be there is the extension has to be asymptotically flat and satisfy the dominant energy condition. Because really we want the mass to have a lower bound in view of the positive mass theorem, we need this dominant energy condition. And also you want some matching condition along the boundary. So this is also called the Bartnik boundary condition. So this is the induced matrix from inside has to match the induced matrix of extended matrix, and the mean curvature has to match. And this pi is the conjugate momentum. That's where I wrote k. So that's k minus trace of k. And this has to match when you're looking at along the normal direction. And the most subtle condition is this has to satisfy the null horizon condition. All right, so roughly speaking, you want to say there's probably no marginally outer trap surfaces in the extension, but there are several various definitions there. I will not go into this exact definition that we put in our results. So this is really abstract definition. And then there's some natural condition questions will come up, right? So of course, in terms of computing, estimate the Bartnik mass, you just need one extension. But in order to really know what the Bartnik mass, you want to say whether there's an extension which realize the infimum. And when the admissible family, when admissible extension realize the infimum, in other words, the ADM mass really is the Bartnik mass of a boundary region, and it's called a Bartnik mass minimizer. And so there is some very natural condition conjectures ask whether a minimizer exists, whether a minimizer is unique, and if the minimizer exists, what property does it have? So he conjectured a minimizer will be vacuum stationary. And so in his paper, he briefly described why he conjectured it to be vacuum stationary. And he said, because that's what we all know for the happen in the positive mass theorem and also in the Penrose inequality. The equality case is realized by either Minkowski or by Schwarzschild, and they both satisfy this property. And there's also related conjecture whether given Bartnik boundary data, you can find vacuum stationary extension. So there are many progress for the Riemannian case. The Riemannian case will assume K here is 0 for the compact set, and then you restrict over the admissible family also has 0K, and the dominant edge condition becomes scalar curvature to be non-negative. Right? And this was already proposed in 1989, but I think it's really probably after Huisken and Ullmann's result, which Professor Huisken talked about, mentioned some earlier in the talk this morning for the Penrose inequality, because their proof of Penrose equality actually strong enough to tell you something about the Bartnik mass, to get estimate of Bartnik mass. And also there are a lot of interesting work by Covino, the one I have been mentioned for the scalar curvature deformation, and from Pengzi, he proved a positive mass theorem with Kohner, so he can show the Bartnik mass has to be non-negative, and by different methods by Shi and Tan, and there are also a lot of very interesting progress. Anderson Curry, Anderson Jurgi, the Montelides Shen gluing, and then extended by Cabrera, Pacheco, Sedabon for the CMC gluing. And also my recent work, we work on the vacuum static extension conjecture. And because this conjecture really has very strong connection to scalar curvature and how it interacts with the boundary geometry, in particular induced matrix and the mean curvature. And people can also ask the question, if you look at extension, which is not asymptotically flat, but asymptotically hyperbolic, then you can also define something, right? And that will relate it to the positive mass theorem in hyperbolic, for the hyperbolic case. So there are also some recent work on this. Cabrera, Pacheco, Sedabon, McCormick, and Daniel Martin, my former student, and my work with Hangchu Zhang, we proved something like a minimizer must be static also in the hyperbolic case. So the rest of the few slides, I'm going to really focus on this vacuum stationary conjecture, which says this is one of the conjecture most well understood in the Riemannian case. And it also seems more like a very natural, right? So if it's a Bartnik mass minimizer, it's vacuum. Initial data set has to be vacuum, and also it's stationary. So stationary will be in a sense, the vacuum development has a global killing vector, and we require the killing vector to be time-like at near infinity. really came to be interested in this conjecture from our earlier work of the equality case. Because in some sense, when we try to prove the equality case, we want to show our initial data set sit inside Minkowski, right? So I think as an intermediate step, probably want to show first initial data set must be vacuum and also stationary, because it's vacuum, it definitely will be stationary, right? But it turns out this very sophisticated work like I mentioned earlier didn't work for the equality case. It turned out we found another proof for the equality case. But fortunately, we can still say something about this Bartnik's vacuum stationary conjecture. So there is some prior results, right? The prior results, as I mentioned, focus more on the Riemannian case because it just happened naturally, has relation to differential geometry with non-negative scalar curvature. And in Riemannian case, Covino already showed a minimizer must be static in this sense. And then earlier we say a static matrix has constant curvature, and because the curvature goes to infinity by asymptotically flatness, so it must be vacuum. So it must be zero scalar curvature everywhere. And there's also a question whether F is positive. So it has been proposed by Bartnik using a different variational method. And so Anderson already carried out a lot, but with boundaries more complicated. But they carry out a lot of variational arguments to show F is positive. They have to modify the admissible. So it's not exactly the same admissible family as I defined earlier. And then Galloway and Null, they studied the zero set of F and also have very interesting results. But then relatively, we knew very little about the conjecture in initial data set. Until very recent, so Covino in 2020, he showed essentially using our local subjectivity and then a conformal type argument to show a minimizer must have the special property. This has non-trivial kernel. And Zhongshan and around the same time, he proved that three-dimensional initial data set, assuming it's vacuum, then he can conclude it's stationary. So it concludes there's a Killing vector field, which is time-like at infinity. So it's based on this variational argument of Bartnik and also Anderson-Jerky for the general initial data set. So here is what we'll get. Right. So, so it turns out the mass minimizer has a very interesting relation to non-improvability. So before we look at the theorem, let's look at this summarized. So essentially, if initial data sets a mass minimizer, even either in the Bartnik mass sense or in the positive mass theorem sense, if it's a mass minimizer, then we know the dominant energy scalar is not improvable. And then now we can use earlier thing, we characterize what non-improvable initial data set will have the property, it has non-trivial F and X satisfy the star system. Then we can say a lot about what the other structure of the initial data set, right? So here the theorem is a general theorem which will imply this observation. So it says if we'll have initial data set which is asymptotically flat and with DC, it can have boundary or without boundary. So either we know the dominant energy scalar is identically zero. In other words, mu equals J, and there's a non-trivial F and X satisfy the star system, or we know if this doesn't happen, the first thing doesn't happen, then we can find the perturbation such that the perturbed data satisfy DC and it actually identically equal to the original one near the boundary. So in particular, all the boundary geometry are the same. But then the energy is strictly less. So we can do that to make linear momentum preserved, but we strictly decrease the energy. So in particular, mass will be smaller. So then if it's a mass minimizer, we know we cannot do the second item. So it must be the first one. So that's the relation between being the mass minimizer in improvability. And then putting this together, we know if we have a minimizer, then we have a non-trivial solution to the system. And then now we can list all the consequences we already derived earlier about having a non-trivial solution to these, which is the dominant energy scalar is constant. So it's 0 in the case of asymptotically flat, and it has to sit in the no dust space-time with the global killing vector. And also we know if it's not vacuum, and then Y has to be null. And then we can see if the mass of this minimizer is strictly positive, in other words, the Bartnik mass is strictly positive, then the initial data set is vacuum. And it actually follows from early observation because the killing vector has an expansion in terms of the energy and momentum by Bike and Kushel. But despite we prove this lot of characterization, there is a dark box. So that demonstrate a dark time in our research is we cannot conclude the mass minimizer is vacuum. We try really, really hard and do all kinds of computations, but we cannot prove it's vacuum. It turns out, we think it should be easier, right? Easier than construct killing vector field, but it turns out to be just, we cannot do that. So that leaves to this one. So let's see. Definitely, I don't want to leave the dark box there, but let's see what we get. Okay, I think just probably one slide. So it turns out there are counterexamples. So the counterexamples are from these PP waves I showed you earlier. So there are the examples which our characterization apply. And in those PP wave spacetime, we can find the initial data set of dimension. And here we have to do the initial data set dimension higher enough, greater than 8, which is complete, asymptotically flat, and have some rate, which I will not have time to talk about. Someone can ask me probably during the question time. And then it has this property, the dominant energy scalar is 0, but it's not vacuum. So in particular, it cannot be Minkowski, right? It's not vacuum. And it has E and P not 0. It also has a global killing vector field that's null at spatial infinity. So those examples really are the counterexample to the equality case of the positive mass theorem without a stricter asymptotically flat decay rates. But as a byproduct, it will also give us the counterexample to the strict positivity conjecture of Bartnik, which say if you have a Bartnik mass 0, then the interior region has to be Minkowski, right? But then it's false because we can just take the interior region of this complete initial data set. And also it will be a counterexample to the Bartnik vacuum stationary conjecture. Okay, so I think I will leave the slides there. I have only a few more, but let me stop here. Thank you.
Thank you very much, Lan. All right, are there any questions?
Thanks for the excellent talk, Lan.
Thank you, Greg. Thank you to see you.
Good to see you.
Well, if there are no questions, let's thank Lan again.
Thank you.
I guess it must have been so clear that.
Right.
All right, we'll see you all in half an hour for Dimitri's talk.